Modern industrial manufacturing relies on brute force. When we need to shape materials or overcome friction, we typically resort to overwhelming physical power. This methodology is often described as heat, beat, and treat. We melt materials at extreme temperatures, hammer them into shape, and rely on reactive, often toxic chemistry to achieve specific properties. Biological systems operate under different constraints. Nature has spent 3.8 billion years of evolutionary research and development refining how physical structures are built without these high-energy inputs. This is the core of morphological engineering. Instead of using thermal or chemical extremes to force a result, biological systems solve structural problems through optimized geometries built at ambient temperature. Overcoming modern industrial bottlenecks does not require generating more power. It requires adopting these superior physical architectures. The popular concept of biomimicry often gets reduced to aesthetic inspiration, like copying the shape of a leaf for a product's appearance. Actual biomimetics is a mathematical discipline. It involves extracting the exact physics, fluid dynamics, and structural ratios from biological organisms for synthetic engineering. These biological models follow two strict thermodynamic rules. They build at ambient temperatures, and they utilize life-friendly chemistry. We can observe this in practice by deconstructing three specific bottlenecks, spanning aerodynamics, microbiology, and thermodynamics, and examining the biological blueprints that solve them. Replacing high-energy chemical solutions with optimized physical geometries aligns human manufacturing with the way nature builds, minimizing waste and energy expenditure by design. The original Japanese Shinkansen bullet train was built for high speed, but its design hit a severe aerodynamic limit. Traveling through narrow tunnels, the blunt nose acted like a piston. It pushed a massive, compressed wall of air resistance immediately ahead of the train. As the train exited the tunnel, that compressed air expanded violently, creating a disruptive acoustic shockwave. Engineers looked to the kingfisher, a bird that routinely transitions between different fluid densities. The kingfisher dives from air into water so efficiently that it enters the surface without displacing mass outward, creating almost no splash. By mapping the mathematical profile of the bird's beak, engineers redesigned the nose of the Shinkansen. Instead of compressing the air, this elongated wedge sliced through the atmosphere, parting the air pressure around the train. The geometric change yielded immediate results. The train ran 10% faster and consumed 15% less electricity. This new shape successfully eliminated the acoustic shockwave at the tunnel exit. Defeating fluid drag in this instance was a problem of geometric proportion, not engine drawer. In microbiology, human industry faces the escalating challenge of biofouling and the spread of superbugs in clinical environments. Hospital maintenance traditionally relies on harsh chemicals to destroy bacterial clusters, but these coatings degrade and can contribute to bacterial resistance. In the ocean, great white sharks remain perfectly clean despite their constant exposure to algae, barnacles, and microbes. The defense is found in the microscopic tooth-like scales covering the shark's skin, called denticles. These denticles form a specific topography of interlocking peaks and valleys, organized according to precise mathematical ratios. This geometry creates a mechanical disruption. The grooves are spaced so that bacteria cannot lie flat or find the anchor points required to form a colony. Material scientists replicated this microscopic geometry in a synthetic material called sharklet. This textured material is applied to high-touch surfaces, like hospital door handles, to block the transmission of superbugs. It maintains a sterile environment through physical shape, removing the need for toxic antibacterial coatings. Structural geometry provides a more sustainable mechanism for defending against microscopic threats than chemical warfare. Harvesting water in a desert requires significant energy to run the industrial pumps and filtration systems needed to process atmospheric moisture. The Namib desert beetle has evolved to harvest water in a climate with almost zero rainfall. During morning fogs, the beetle stands on its head at the crest of a sand dune, intercepting fog as it rolls past. A microscopic cross-section of the beetle's carapace reveals a specialized surface for manipulating fluid dynamics. The peaks, shown here in blue, are hydrophilic. They attract and accumulate microscopic moisture from the passing air. The valleys, shown in orange, are hydrophobic. Once a droplet on the peak becomes heavy enough, it slips into these frictionless channels. This bifurcated surface chemistry routes the condensed water directly into the insect's mouth, providing hydration without any energy expenditure. Engineers have developed fog-harvesting meshes and tents based on this alternating texture. These materials allow people in arid regions to extract clean drinking water from the air without relying on a power grid. Manipulating surface chemistry at the microscopic level can replace the need for energy-heavy industrial pumps. The aerodynamics of the Shinkansen, the sterility of the sharklet surface, and the beetle's water collection all lead to the same conclusion. None of these industrial bottlenecks were resolved by increasing energy output or synthesizing harsher chemicals. Modern heat, beat, and treat manufacturing is a linear process that requires high energy and results in a cycle of waste. Nature, however, uses shapes that allow materials to be reused or safely integrated back into the environment. By prioritizing physical shape over chemical alteration, morphological engineering allows us to adopt this same efficiency, reducing the environmental and energetic cost of everything we build. The takeaway from 4 billion years of evolution is that highly efficient systems are built at ambient temperatures, using life-friendly building blocks. The natural world is an actively optimized engineering database. When faced with a technical barrier that brute force can no longer overcome, the solution is often found in these biological blueprints. Integrating biological physics into our industrial infrastructure provides a strategic path toward achieving higher efficiency with a lower energy footprint.